August 1347, somewhere in the limestone hills of Provence. Outside, the Mediterranean sun beats down at 95 degrees Fahrenheit, turning the dusty roads into shimmering ribbons of heat. Cicadas drone in the olive groves. Even the lizards have retreated to the shadows. But inside a 2-story stone house in the village, a merchant's family sits comfortably in their main hall, eating bread and soft cheese without breaking a sweat. The children play on the flagstone floor. No one is fanning themselves. No one is complaining about the heat. The interior temperature hovers around 68 degrees Fahrenheit, a full 27 degrees cooler than the inferno outside. Walk into a modern suburban house on a similar summer day, and you'll find a very different scene. The AC unit rattles and hums, struggling to keep the indoor temperature below 78 degrees Fahrenheit. The electricity meter spins. The power bill climbs. Turn off the AC for an hour, and the house becomes uninhabitable within minutes. The thin walls, the large windows, the flat roof, everything about modern construction seems designed to trap heat and cook the inhabitants alive. We've built homes that require constant mechanical intervention just to remain livable, while medieval builders created structures that regulated temperature through pure physics and intelligent design. The question isn't just how they did it. The question is why we forgot. The secret starts with the walls themselves. A typical medieval stone house in southern Europe had walls between 18 and 36 inches thick. Not because the builders were wasteful or didn't know how to calculate structural loads, but because they understood something modern construction has deliberately ignored. Thermal mass is the cheapest air conditioning you'll ever install. Thermal mass works on a simple principle. Dense materials like stone, brick, or rammed earth absorb heat very slowly. When the sun hits a 24-inch thick limestone wall at dawn, the heat begins penetrating the outer surface. But it takes hours, sometimes an entire day, for that heat to work its way through the mass of stone and reach the interior surface. By the time the heat finally penetrates to the inside, the sun has set. The outdoor temperature has dropped, and the wall starts releasing its stored heat back to the exterior through the cool night air. The interior surface never gets hot. Medieval builders didn't have thermometers or heat transfer equations, but they had centuries of empirical observation. They knew that the old Roman villas stayed cool in summer, and those villas had thick walls. They knew that castles built with massive stone blocks remained comfortable, even during siege warfare in July. They knew that granaries with thick walls kept grain from spoiling in the heat. So they built thick, and they built with stone. The physics is elegant. Stone has a thermal diffusivity, the rate at which temperature changes propagate through a material, that is roughly 1/10 that of modern drywall and insulation. A 24-inch stone wall doesn't just slow heat transfer. It creates a thermal lag of 12 to 16 hours. The house responds to yesterday's weather, not today's. When you're living through a heat wave, that lag becomes a blessing. The house interior remains cool even as the outside world bakes, because the walls are still releasing the mild temperatures from the previous night. Modern construction inverted this wisdom. We build with wood frames, thin brick veneers, and drywall materials with almost no thermal mass. A standard modern exterior wall might be 6 inches thick total, with most of that volume occupied by air gaps and fiberglass insulation. Insulation slows heat transfer, yes, but it does nothing to absorb and store thermal energy. The result is a house that responds to temperature changes within minutes. The sun comes out, the house heats up. The sun sets, the house cools down. Without mechanical climate control, modern homes are thermal roller coasters. The medieval approach had another advantage. It worked both ways. In winter, those same thick walls absorbed heat from the central hearth and radiated it back into the living spaces for hours after the fire died down. The house became a thermal battery, storing warmth during the day and releasing it through the cold night. One good fire could keep a room comfortable for 12 hours or more.
But thick walls alone weren't enough. Medieval builders also understood solar orientation in ways that would shame most modern architects. Walk through any surviving medieval village in southern Europe, and you'll notice something. The houses don't face random directions. The main facades face north or northeast. The small windows face south. The blank walls face west. This wasn't aesthetic preference. It was thermal strategy. The south-facing wall receives direct sun for most of the day in summer, especially at the high solar angles typical of Mediterranean latitudes. A large south-facing window becomes a solar oven, flooding the interior with radiant heat. Medieval builders knew this, so they kept southern exposure small. 1 or 2 narrow windows for light, placed high on the wall where the summer sun's steep angle would send most of the light bouncing off the sill rather than penetrating deep into the room. The west wall was even more critical. In summer, the afternoon sun strikes western walls at a low angle, hitting the surface nearly perpendicular, and delivering maximum thermal radiation precisely when the day is already at its hottest. Medieval houses in hot climates often had no windows at all on the western wall, just solid stone, sometimes whitewashed with lime to reflect rather than absorb solar radiation. Meanwhile, the north side stayed shaded all day in summer. This is where builders placed the main entrance, the larger windows, and sometimes even covered porches or loggias. Cool air entering from the north could flow through the house without being preheated by solar radiation. The building became directional, channeling the coolest available air into the living spaces. Window size tells the same story. Medieval windows in hot climates were small, often just 18 to 24 inches wide, even in wealthy homes. Not because glass was expensive, though it was, but because large windows are thermal liabilities. Glass is a terrible insulator. A large window is essentially a hole in your thermal mass. Summer sun streaming through a big window heats up floors, furniture, and walls directly, bypassing all the benefits of thick stone construction. Medieval builders understood this trade-off. They accepted dim interiors as the price of cool interiors. Modern architecture does the opposite. We worship natural light and panoramic views, so we install enormous windows facing every direction. South-facing glass walls, west-facing picture windows, floor-to-ceiling glazing. Then we wonder why our cooling bills are astronomical and our AC units CA and keep up on hot afternoons. We've prioritized aesthetics over physics, and we pay for it every summer.
The third piece of the puzzle was the wall finish itself. Medieval stone houses weren't just stone. The interior walls were covered with lime plaster, sometimes multiple coats, sometimes up to an inch thick. The exterior walls were either left bare stone, whitewashed with lime, or finished with lime render. And lime changes everything. Lime plaster is hygroscopic. It absorbs moisture from the air when humidity is high and releases it when humidity drops. This creates a passive humidity regulation system. On hot summer days, as people sweat and cook and breathe inside the house, the lime plaster absorbs excess moisture, preventing that clammy, sticky feeling you get in humid heat. As evening arrives and the air dries out, the plaster releases moisture back into the air, creating an evaporative cooling effect on the wall surface itself. The interior feels cooler, not just because the temperature is lower, but because the humidity is regulated. This is a type of cooling modern HVAC engineers call latent cooling, cooling that comes from controlling moisture rather than temperature. Medieval builders achieved it with plaster. We achieve it with dehumidifiers and multi-stage air conditioning systems. The lime exterior finish had a different purpose: reflection. Lime wash is intensely white when fresh, with a reflectivity that approaches 90%. A whitewashed stone wall reflects most of the sun as radiation back into the atmosphere before it can be absorbed as heat. The wall surface stays significantly cooler than it would if left as bare stone. In the blazing sun of a Greek island or Spanish village, that reflective white surface could be the difference between a tolerable house and an oven. Medieval builders in Mediterranean regions reapplied lime wash every year or two, maintaining that brilliant white surface, specifically to combat summer heat. It was cheap, it was effective, and it required no technology beyond a bucket and a brush. Modern construction uses different materials. We seal our walls with latex paint, vinyl wallpaper, and impermeable vapor barriers. These materials don't breathe. Moisture gets trapped inside walls, leading to mold and rot. We can't use evaporative cooling through our wall surfaces because we've deliberately made those surfaces non-permeable. Then we spend thousands of dollars on mechanical ventilation and dehumidification to solve the problems we created. The irony deepens when you look at modern, breathable building materials. We now manufacture expensive hygroscopic plasters and specialized lime products marketed as high-tech, green building solutions. We're literally reinventing medieval plaster and selling it as innovation. Walk into a medieval stone house, and one of the first things you'll notice is the ceiling height. Not the cramped 8-foot ceilings standard in modern construction, but soaring spaces 10, 12, even 14 feet from floor to ceiling in the main rooms. This wasn't grandeur for its own sake. It was thermal engineering. Hot air rises. This is perhaps the most basic principle of natural convection, and medieval builders exploited it ruthlessly. By creating tall interior volumes, they ensured that the hottest air in the house would stratify at ceiling level, well above the heads of the inhabitants. The air you breathe, the air at table height, the air where children play on the floor, all of it stays cooler because the hot air has somewhere else to go. But high ceilings alone create a problem. How do you get rid of that accumulated hot air? Medieval builders solved this with roof vents, cupolas, and strategically placed openings at the highest point of the structure. Many medieval houses had small openable hatches or louvers in the ceiling or roof peak. On hot days, you'd open these vents and let the hot air escape by natural convection. Cool air would be drawn in through lower windows or doors to replace it, creating a passive ventilation loop. Some medieval buildings took this principle further with ventilation towers, vertical shafts built into the structure that acted as thermal chimneys. The physics is simple but effective. As hot air rises through the tower and exits at the top, it creates negative pressure at the bottom, drawing cool air in through ground-level openings. No fans, no electricity. Just hot air rising and pulling cool air behind it. The roof structure mattered too. Medieval roofs were often steeply pitched, with substantial air gaps between the ceiling and the roof surface. Clay tiles or slate created an additional thermal barrier. The sun would heat the roof surface to 140 degrees Fahrenheit or more. But that heat was radiated into the attic space, a buffer zone that insulated the living spaces below. Ridge vents or gable vents allowed hot air to escape from this buffer zone, preventing heat buildup. Modern construction, especially in the post-war suburban housing boom, abandoned these principles. We build with flat or low-pitched roofs that sit directly on ceiling joists, creating no air gap and no thermal buffer. We've standardized 8-foot ceilings to minimize construction costs and heating expenses. Never mind that those same low ceilings trap hot air at head level in summer. We seal our houses tight for energy efficiency, preventing natural ventilation, then run electric fans and AC units to move air artificially. We've traded passive physics for active machinery. Medieval builders in hot climates understood another cooling principle: evaporation. Water evaporating into air absorbs massive amounts of heat, roughly 540 calories per gram of water vaporized. If you can get water to evaporate inside or near your house, you can cool the surrounding air dramatically. Wealthy medieval homes in Mediterranean and Middle Eastern regions often included interior courtyards with fountains or shallow pools. These weren't just decorative. The fountain created a continuous evaporation surface, cooling the air in the courtyard by several degrees. That cooled air would then flow into the surrounding rooms through windows and doors facing the courtyard. The effect was powerful enough that even modest homes would sometimes have a large ceramic pot filled with water placed near windows or doorways, relying on slow evaporation from the pot surface to cool incoming air. The courtyard design had another benefit. It created a microclimate. The courtyard walls shaded the interior space during most of the day, preventing direct sun exposure. Any breeze flowing over the courtyard would be funneled down into the space, creating air movement even on still days. The combination of shade, evaporative cooling, and funneled airflow could make a courtyard 10 to 15 degrees cooler than the surrounding streets. Medieval Islamic architecture took this principle to extraordinary heights, with wind catchers, tall towers, with directional openings that captured even slight breezes and directed them down into the building. These towers often incorporated water channels or wet fabric screens, so the captured wind would blow across evaporating water before entering the living spaces. The result was genuine evaporative air conditioning, powered entirely by wind and water. Even in northern Europe, where summer heat was less intense, medieval builders used water for cooling. Large houses and castles often had cellars with channels for small streams or springs running through them. The flowing water kept the cellar cool, and the cool air from the cellar could be drawn up into the house through vents or stairwells. Food storage rooms were deliberately placed above or adjacent to these cool cellars, taking advantage of the temperature gradient. Modern construction largely ignores evaporative cooling, at least in humid climates where it's less effective. But even in dry climates where evaporative cooling works brilliantly, we've abandoned these passive techniques in favor of refrigerative air conditioning. We've lost the knowledge of how to position a fountain for maximum cooling effect, how to design a courtyard that creates its own microclimate, how to channel wind through a building to create cross-ventilation. We rely on compressors and electricity instead. Medieval stone houses didn't just stay cool in summer, they adapted to the seasons. The inhabitants used simple, reversible techniques to modify the building's thermal behavior, depending on the time of year. Exterior shutters were perhaps the most important seasonal tool. Medieval shutters weren't the decorative vinyl panels we mount on modern houses. They were solid wood, sometimes 2 or 3 inches thick, with adjustable louvers or solid panels. During summer, inhabitants would close the shutters during the hottest part of the day, particularly on south and west-facing windows. The shutters created a shaded air gap between the window and the outdoor environment, preventing solar radiation from hitting the glass or wall surface directly. At night, they de-open the shutters to let cool air flow in and flush out the day's accumulated heat. In winter, the same shutters stayed open during the day to admit precious sunlight and solar heat, then closed at night to provide an additional layer of insulation against the cold. The shutters converted the house from summer mode to winter mode with no permanent changes, no renovation, just daily adjustments based on weather. Interior fabric played a similar role. During winter, medieval homes would hang heavy wool or linen tapestries on the walls, creating an air gap that provided insulation. Come summer, those tapestries came down, exposing the cool stone surface and allowing the thermal mass to work unimpeded. Rugs appeared on floors in winter and disappeared in summer. Furniture moved closer to the hearth in cold months and dispersed to shaded corners when heat arrived. Some medieval houses in hot climates used temporary awnings or canvas shades during the worst of summer. Fabric stretched over courtyards, across windows, or along south-facing walls created shade without permanent structural changes. When soaked with water, these canvas shades provided evaporative cooling as well. Come autumn, the canvas came down and went into storage. This seasonal intelligence extended to daily routines. Medieval households in hot climates shifted their activities to match the thermal conditions. Heavy work, cooking, and chores happened in the early morning or evening when temperatures were lower. The middle of the day was for rest, light work, or activities in the coolest parts of the house, often the cellar or north-facing rooms. They worked with the building's thermal rhythm rather than trying to override it. Modern life has largely abandoned this flexibility. We build houses that are supposed to maintain the same temperature year-round, day and night, regardless of outdoor conditions. We've removed the seasonal intelligence from our homes and replaced it with thermostats and HVAC systems. We've gained convenience and lost adaptability. The question haunts every summer heat wave. If medieval builders could keep stone houses cool without electricity, why can't we? The answer isn't that we lack the knowledge. The physics of thermal mass, solar orientation, and natural ventilation are well understood. Architecture schools teach these principles. Green building advocates promote them. The information is there. We simply choose not to use it. Modern construction is optimized for speed and cost, not thermal performance. A wood-framed house can be erected in weeks. Thin walls require less material and less labor. Standardized designs don't require site-specific analysis of sun angles and wind patterns. Large windows sell houses to buyers who value views and natural light over energy efficiency. Every decision makes sense from a business perspective, and every decision sacrifices thermal performance. Building codes compound the problem. Most codes specify minimum insulation values but say nothing about thermal mass. A house with R30 insulation in thin walls meets code, even if it has 0 thermal mass and will heat up like an oven in direct sun. Codes mandate energy efficiency in terms of heating and cooling loads, which encourage builders to seal houses tightly and install bigger HVAC systems, rather than designing buildings that need less mechanical climate control in the first place. Zoning regulations often prevent the dense, shaded, courtyard-oriented layouts that worked so well in medieval villages. Setback requirements force houses into isolation, eliminating the mutual shading and wind channeling that occur in traditional street layouts. Minimum window area requirements ensure that houses have adequate natural light, even if those windows compromise thermal performance. We've codified thermal dysfunction into law. Then there's the aesthetic problem. Medieval stone houses look old. They have small windows, thick walls, and irregular proportions. They don't photograph well for real estate listings. They don't match modern expectations of what a house should look like. Even people who understand the thermal benefits of thick-walled design often can't bring themselves to build that way because the result looks too different from the suburban norm. The final issue is economic. Thermal mass has high upfront costs and long-term benefits. Building 24-inch thick stone walls costs more than building a wood frame with vinyl siding. But over the life of the building, the stone walls require far less energy for cooling, cost less to maintain, and last several times longer. The problem is that developers build houses to sell quickly, and buyers rarely calculate lifetime costs. The upfront price dominates the decision, and the cheap modern construction wins every time. We've created a system that selects against good thermal design at every stage, and then we act surprised when our houses can't stay cool without air conditioning. But the knowledge isn't lost, it's just underutilized. Small movements in architecture and building design are rediscovering these principles and applying them to modern construction. Passive house standards emphasize thermal mass and airtight construction. Earthship builders create modern versions of thick-walled, thermally massive homes using tires and earth. Adobe construction is experiencing a revival in the American Southwest. These approaches are marginal now, but they prove the principles still work. Individual homeowners can apply some of these lessons even to existing modern houses. Adding thermal mass to a house is difficult, but not impossible. A thick tile floor over a concrete slab adds thermal mass at ground level. Interior stone or brick walls can be installed as features that also serve as thermal batteries. Even filling interior walls with sand a technique some DIY builders have experimented with adds some thermal mass without major reconstruction. Exterior shutters are easier. Real shutters, not decorative ones, can be added to most houses. Closing them during peak sun hours reduces cooling loads dramatically. The effect is immediate and requires no renovation, just a change in daily habits. Strategic planting can modify a house's solar exposure. A deciduous tree on the south or west side of a house provides shade in summer when the tree has leaves, but allows winter sun through when the tree is bare. Vines on a trellis can shade a wall or window without permanent structural changes. These biological solutions take time to grow, but they're cheap and they work. More ambitious homeowners can modify roof structures to add ventilation and thermal buffering. Ridge vents, gable vents, or even a simple operable skylight can allow hot air to escape from the upper levels of a house. Painting a roof with reflective coating reduces solar heat gain. Installing a radiant barrier in the attic creates an additional thermal break. The larger challenge is cultural and economic. We need to rebuild the understanding that houses should be designed for their climate and location, not mass-produced from standardized plans. We need building codes that reward thermal mass and passive cooling, not just insulation, our values. We need a generation of architects and builders who understand these principles and can apply them to modern construction. And we need buyers who value long-term performance over short-term aesthetics. Medieval builders didn't have perfect knowledge. They never calculated heat transfer coefficients or ran computer simulations of airflow. But they had empirical wisdom accumulated over centuries of building in hot climates without mechanical cooling. They understood that a building is a partnership between structure and inhabitant, between stone and sun, between design and daily practice. They built houses that breathed with the seasons, responded to the sun, and created comfort through physics rather than machinery. We abandoned that wisdom in pursuit of speed, cost, and aesthetic fashion. Now, as energy prices rise and climate change intensifies summer heat, we're discovering that medieval builders knew something worth remembering. Thick walls work, orientation matters, evaporation cools, stone lasts. The principles haven't changed, only our willingness to use them.